L isn't 0, yeah. All right, so we're talking about basic subspaces that come directly from a matrix. So recall from last time, this is a recall from last time. So we're recalling from last time, and last time we recalled from last time when we asked ourselves what a column space, row space, and null space are. A column space is essentially the subspace that's spanned by the columns of a matrix. A row space is essentially a subspace that's spanned by the rows of a matrix, and the null space is going to be the subspace that is, I wouldn't say spanned by, but the subspace that is a solution to the homogeneous system where the matrix is your coefficients, matrix of coefficients in your system, and it's all set equal to 0. The null space, as an aside, the null space is sometimes called the kernel, K-E-R-N-E-L. And if you do more math stuff, you'll see the word kernel pop up in a bunch of different places. But I think if you're not a math major, you're just like a computer science or engineer or physics or whatever. I don't know if kernel is going to pop up so much. Pop up. Like popcorn kernel. Get it? We're just full of it here. All right. So we have our example over here where we found the null space, and then it turns out that one of the theorems tells us easily how to find the column space, easily after you've row reduced it. I suppose the row reducing part is going to be the more difficult part. But once you've row reduced it, the null space takes a little bit of work because you're going to have to figure out the free variables and set up your equations. But the column space, all you have to do is identify your pivot columns. And once you have your pivot columns identified, then you go to the original matrix. You go to the original matrix and you identify those pivot columns, and those will be the basis. Speaking of basis, a basis of a subspace is a set of linearly independent vectors that span the whole thing. Okay? This is the minimum amount of vectors you can have to describe the whole subspace. All right? So to try to make that idea make more sense, I'd like to take a look at some of our examples of the subspaces. Good thing we typed it up, huh? We had a couple of subspaces, or we have a couple of vector spaces that we looked at. So we looked at Rn. We call that example 0, I think. And then we looked at the vector space of all polynomials. And then we said that a polynomial, the set of all polynomials that's degree 2 or less is a subspace. And we showed why that was. And we took another tour of a different sort of vector space, and that's the GF2. By the way, I remember that sometimes a GF2 is described as a GF2 is sometimes denoted as the Z with the double bars. In math, they use the z for integer. Anybody speak German? How do you say integer in German? I don't know. It starts with a z. Zinteger. So, what? Zahlen? So that's it came from the Germans. Usually, a lot of the stuff comes from Latin, but this particular symbol came from the Germans. So this z is a set of all integers in math. So z sub 2. So z sub z sub 2 is the set of integers that only has 2 elements in it. And there's a z5 that has 5 elements, 0, 1, 2, 3, 4. That's z5, and then z whatever. You can look at the clock and call that z12. No, I'm just making an example of a clock. So in I think in grade school they talk about clock arithmetic in math, where you only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 as your numbers, and you would add, 6 hours from 11 o'clock is not 15, but 6 hours from 11 o'clock is 5 o'clock. Had to do that math. So it's similar to the z sub. There you go. That's what happens. And so if the teachers only knew that they were talking about z12 back then you guys might have been more advanced than that. But anyways. Yeah, I know, huh? I didn't mean to. Sorry. Anyways, we had a couple of examples for the GF2 field, or the vector space that has the 3 components. We start off with a really simple, and I think we called this, I don't know if we call this a degenerate subspace, but it's just a subspace with just 0 in it. So a subspace has to have 0. If you have a subspace with just 0 in it, technically that's a subspace, right? It's a subspace. It's a boring subspace, but it's still a subspace. So that's 0 subspace is a subspace for any vector space that we talk about. In our second example for GF2, we came up with an example that's not a subspace. It's not a subspace because if it's a subspace, we're supposed to be able to add a couple of elements and then get another result that's supposed to be in that subspace, but it wasn't for these 2 elements that we added. So it's not a subspace. In our third example, we did find this to be a subspace because if we added any combination of these 2 or itself, we're still going to be within the subspace. And if we scalar multiply this, and our scalars are just 0s and 1s, if we scalar multiply this, then we're still going to be in the subspace. So this is in fact a subspace. We also found another thing that's a subspace as well. So these are all subspaces of vector spaces. And as we're talking about these theorems, we're focused on the column, the row, and the null space. But let's talk about this idea of a basis, a set of linearly independent vectors that span everything. And again, what I want to stress is the fact that the basis is the smallest set of vectors to describe your subspace. All right, new page. Let's talk about basis. It has to span the entire subspace. So in Rn, in our basic example of Rn, uh-oh, we're going to have this issue again. Can't write. Oh, boy. I thought this had the default already. Oh, that sucks. Oops. Uh-oh. I gotta fix that. Anyways, for some reason my pen's not writing properly. I suppose. What if I do this? I'll I'll just type it up. Is that annoying? The typing? I mean, the notes are a lot more readable, right? Type it. Well, it does lack character. Because I could just give you my notes and then that would be it. Then I don't even have to lecture anymore. Oh, cool. All right. Let's take a look at v equals. Let's go to Rn, and we had a couple of really simple examples of vector spaces, and we said, or subspaces. We said that 0 is a subspace. Let's call it H0 equals the 0 vector. And I suppose we should denote this as a vector. So that's going to be, depending on if we're in R2, then that's 0, 0. And if in R3, that's 0, 0, 0. If we're in R5, that's 0, 0, 0, 0, 0, 0. So it's essentially the origin of wherever you are. And this is a subspace. We know that this is a subspace. So the question is, what is a basis for this? 0. So the basis is supposed to be the smallest set of vectors that you would need to span this thing. Well, this is kind of like a trick question because the basis is not exactly 0 because 0 doesn't span anything, right? Yeah, well, that's like saying that's the vector 0. But again, 0 still doesn't span anything. The basis of this is nothing. It's the null set. And the null set is a set with nothing in it. It does exist. Actually, in math, they sometimes call it, let's see if this will work. Null set. Nope. Nothing. Nope. It's this. Where is it? You guys see a null set? Null. Here it goes. Empty. Empty set. There you go. So sometimes this is what denotes a null set. So in this case, the basis is nothing. Let's see, H. Let's call this Hn. And we said before that that the whole vector space is can also be considered a subspace, right? So what is a basis for Rn? Do you guys know? Do you guys remember? What? No. Yeah, so actually we have another name for that. The basis vectors, that's the other name for that. E, we called it E. Yeah. You sound so disgusted. Oh. I know what you meant. What? Yeah. So your set that has, 1, 0, 0, 0, 1, 0, 0, 0, 1 for R3, for example, that is your general set of vectors. Okay. So these are examples of basis. Now, let's do another example with R something else. But before we do that, let's do an example from the other two vector spaces that came up with. So a basis is the smallest number of vectors you need to be able to span the space that you're looking for. And by span, I mean a linear combination of things. So that means if I'm spanning a set of something, my subspace, then there's a point in the subspace I want to get to. I can use my basis vectors to get there. And the basis vectors, again, is the smallest number of vectors you need to be able to span everything. Okay, so let's first talk about the two examples, since we did spend some time talking about those two examples, the polynomials, and then the GF2, and then we'll find more concrete examples that we can actually hold on to and visualize. So more examples here. Let's take a look at our V equals a set of polynomials. I don't know if did we call it anything? Polynomials. All right, so I think we had a subspace. Well, let's take a look at the whole set, the whole subspace. Let's say H equals the whole vector space. Let's call it V for the whole vector space. All polynomials. So how many? I'm sorry. Maybe before we do this, let's talk about the smaller subspace that we did find. So let's call this H sub P sub 2 to be the subspace of polys of degree 2 or less. So these are going to be your polynomials that's either a quadratic or a linear or constant, or maybe zero. Zero is a constant. Let's talk about finding a basis for this. So let's imagine what we need to create a polynomial, a quadratic. Let's imagine what we need to create a quadratic where we can add them and scalar multiply them. I don't know if that question made sense, but can somebody try to answer? I don't know if I can repeat it. What do we need to be able to create a polynomial of degree 2 or less where we would just add it and scalar multiply it, and we would cover every single one of those types of polynomials? Andrew had his hand up first, and we'll see if you're matched. What? Okay, you're unputting your hand up. Matt, you want to take a guess? And then. In general, your quadratic is of the form ax squared plus bx plus c. Keep going. You're there, except you kind of pulled away from it. You have an x term and a constant. Yeah, yeah.
And you could create span of two separate equations.
Okay. You're close. You missed when you said two things. You missed one. Pedro, do you want to say something? Okay. Andrew and then Alan. Close. Close. Hold on. Let's see what Alan has to say. Like what? Right. So ax squared bx plus c is your generic quadratic, right? But the a, b, and c, this is I think where you were trying to get at with c, are just the constants or scalars, right? And so if I want to just ignore those scalars, and we get to add them up anyways, what's left when you ignore those scalars? Oh, I should do this in. There. Now if I take these and span it, right? That means I just multiply each one of these by a scalar, and then I add them, ax squared plus bx plus c. That's about as generic as you can get. Any one of those can be 0 or non-zero, doesn't matter. If they're all equal to 0, then we have the 0 polynomial, which is part of our subset, right? And we scale them and we can add them and it would still be within the subset. But now this is my basis. Did you think about this, Brandon? Your face lit up somewhere in our discussion, and then I wanted to ask you, but yeah. I don't know. So the span of these, now remember that these elements are technically called vectors, right? The span of these things, you know, if I switch to order, might look like a x squared plus bx plus c. I mean, we could put a1, a2, a3, or a sub 2, a sub 1, a sub 0, but regardless, the ABCs are just the constants or the scalars that we're using to multiply them. But if we use 1x and x squared as a basis, then we have everything we need to be able to write anything in this subspace as a linear combination of these three things. Okay? So if we're talking about the entire subspace, entire vector space, the basis would probably look like 1x, x squared, x cubed, dot, dot, dot. We go on forever. Okay? Yeah. Well, there's no special name for it. But it's an infinite dimensional. So the number of bases, by the way, which we'll get to, the number of basis vectors you have will be the dimension. So we have an infinite dimensional vector space. Cool, huh? The set of polynomials is an infinite dimensional vector space. It does, but it's really nothing. You can pretend you're smart. Yeah. So right. So when you go to a bar and you want to meet somebody, say, hey, I know an infinite dimensional vector space. Might work better at a college town like Santa Cruz. Worked for me, I don't know. Oh no. I never did any of that. Right. All right, so our third one is our GF2 example. So let's take a look at some of the subspaces, or one of the subspaces that we came out of there. So we know that the 0 is not a subspace. Here are a couple of examples that turned out to be subspaces for us. And let's see if we can tease out, see if we can tease out the basis vectors for each of these examples. So in our example here, GF2, we had an example where we found a subspace, and because this is a finite set, we actually can list down the subspace. And so we only have two elements in the subspace, the 0 vector, which always has to be in a subspace, and then the vector 1, 1, or 1, 0, 0. So let's see if we can find a basis for this. So the basis for this is going to look like, well, we have these two vectors. Why not just use those two vectors as your basis? Actually, are you typing this? Because don't. This is not quite our basis vectors. Basis vectors is a list of vectors, the minimum number of vectors that span the whole thing. So what's wrong with this set? Yes. They're linearly dependent. We need to get rid of one of them. Which one? The 0 vector. There you go. This is our subspace. This is the basis for a subspace. All we need is this to be able to span my whole space. Yeah. By span, I mean write this as a linear combination to get everything else in my subspace. So write this as a linear combination scalar multiplied linear combination, right? So in this example, I only have a finite number of elements in my subspace. I only have 2, right? So the question is, can I take this basis? I only have one thing in my basis. Can I take that one vector and scalar multiply it or add it with itself so I can get both of these? And the answer is yes, right? If I take that one basis vector and I multiply this by 1, then I get this vector. If I take this basis vector and multiply it by 0, then I get the other one. Well, that's all I really need because I have a finite number and I'm done. So that's all you need for the basis. What do we have now? Again, we're jumping ahead to dimension, but we have a one-dimensional subspace of this vector space. Oh, it's the dimension, which we haven't defined yet formally. The dimension is the number of basis vectors I have. I don't know. We'll take a look at it. But yes. Here's my other subspace. This looks like it's a proper subspace. A proper subspace, by the way, is a subspace that's not everything. Because everything can be a subspace, right? So if I don't include everything, then it's called a proper subspace. So here we have another subspace. What's my basis for this? Only two? The zero vector can go away, right? But I have three others past the zero vector. So Pedro said 1, 0, 0, and 0, 1, 0. How about that last one? Should I add that last one? She said it. But thanks, guys. So Sebrian said, the last one is a linear combination of those two vectors already, and so we don't need to add that. That's just redundancy. We don't want redundancy for our basis vectors. We just want the smallest amount of vectors that's going to span everything in there. Okay? So that's it. We have a two-dimensional vector space, subspace. Right? Well, in this case, they're in GF2, 3. Because we're not talking real numbers here. We're just talking about these two elements, 0 and 1. Yeah. Yeah. In the subspace, yes. Okay. All right. Now, if we take a look at the whole space, which is also a subspace, it's not a proper subspace, but it is a subspace. And Ali already answered this question. We actually listed this down, didn't we? Or was it? There he goes. So if we want to look at this whole thing and find its basis, then the basis is going to be, well, it shouldn't be the whole thing, right? We just need representatives that would be able to represent every single one of these vectors. And so we know that the zero vector is gone. And from the last example, 1, 1, 0, we can get by adding 1, 0, 0, and 0, 1, 0. So we can get rid of that. Can we get rid of anything else? Yeah, so the other ones can be linear combinations of these first three. So Ali concluded that this is actually a three-dimensional subspace of the vector space. And when you're talking about dimension, you're talking about the number of basis vectors. We have 3 basis vectors, which is similar to the ijk vector if you're in R3. But this will work. So we have our basis vectors. Okay, is that cool? It would, that means that to be able to get any of these vectors in GF23, all I need is these 3 vectors from the basis and any linear combination of them. So I can either multiply them by 0 and or 1 and then add these things. Like to be able to get this vector in my GF23 vector space, I would need to add the first vector in the basis and the last vector in the basis, and then I have that. So I don't need to include 1, 0, 1 in my basis vectors because I have 2 others that can represent that. Okay? Yeah. Okay. This, yeah, the smallest amount. Okay, good. All right, so let's see if we can actually formally define Well, 2.9 talks about coordinate system and dimension. So let's talk about those first. And the idea of a coordinate system might be clearer after we take a look at a few more examples of things. I don't know. So suppose a set B, that's B1 through B, I don't know, P or something, is a basis for a subspace H. That means if it's a basis, then each element in H can be written as a linear combination of all those basis vectors. And then they have these things called weights, C1 through CP, and we defined weights already. They're really the coefficients, the scalar multiples that we're tacking on to the vectors before we add them up. And then we can make a vector out of that, C1 through CP, and that's called a coordinate vector of x relative to your basis. So let's do a simple example of this. And just stick with R2. We have our basis vectors to be, what is it? That's 0, 1, and 1, 0, the I and J. Is it okay if I use I and J? You guys are all cool with that, right? 1, 0, and 0, 1. So those are the ij vectors. Those are the basis vectors. Now, if you give me any point or any vector, technically a vector, but it's really a point. If you give me any point in R2, can be written as a linear combination of I and J, right? So let's do an example. What's an example? Can you give me any point in R2? One comma what? Let's do -3 comma 4. Right? So -3 comma 4 can be written as a linear combination of I and J. -3I plus 4J. Well, that's kind of boring. Well, they're all kind of boring. And so we can write this. We can therefore write this as the vector with -3 comma 4, or -3 not comma, but as a column vector. With respect to the basis. And usually, if we're talking about the standard basis, then that's not a big deal. know, they would pull this subscript over here called B. So that was a boring example. Let's shake it up a little bit. Let's change our basis vectors instead of just the I and J. So it turns out that if you have any two vectors that are linearly independent in R2, then that would be able to span all of R2. So I have one vector here. Can you give me another example of a vector that's linearly independent from 1, 1? 3, 2. It's linearly independent from 1, 1. Right? Oh, maybe I should have picked an easier one. All right, I'm going to change this. 0, 2. 6. No. No. Wait. There's no problem. 6. What? I'll just pretend I just randomly made it up. Okay. So I'm just randomly making up some vectors here, right? And so now I'm going to call this, since this is not the standard basis, I can call this another basis. Let's call it, I don't know, what should we call it? Let's call it script B. What? Or the fancy looking B. So let's say this is a basis vector for me. Okay? Are we good so far? So this should be, I mean, if we did this right, and by right, I mean the only thing we need to check is that they're linearly independent. Because there's two of them, and we know that R2 is a two-dimensional space. So if we did this right, then every single point in R2 can be written as a linear combination of these two vectors, correct? So let's take the example that we got. Can we write this as something times our first vector plus I'm going to have issues because I have an underscore. I'll just say C1 times this vector plus C2 times this vector. And by these vectors, I mean these vectors that we came up with in our as our basis. So, can we? So we can, normally we would have to do, solve for C1 and C2 and set it equal to -3, 4. But what's C1 equal to? And what's C2 equal to? See, that's why I was trying to figure out what a good number would be so that we can come up with easy numbers. Or I can just say, hey, look, well, that was easy. It wouldn't have been that easy. Okay? Yeah, if it wasn't that easy, then you just have to do a quick system. It's only a 2 by 2, but you know, it's still, let's not worry about that. So what they're saying is that I can represent this point or this vector, pointer vector, it doesn't really matter, as the weight of these things. See these coefficients? 1 and -1. So I can write it as a vector that's 1, -1. Wait, but that doesn't make sense because 1, -1 is another point or another vector. So to make sure that we're distinguishing this from a regular vector in standard with standard basis, we're going to use a subscript. That to say my basis that I was using to get this is actually the basis that we made up. Yeah. Made up. We made it up. That's -3,4 is a coordinate in the standard basis. If we want to look at that as a vector in our standard basis, it's -3,4. Yeah. Okay. Yes. Yes, more or less. But here they're talking about a switch of bases. And the way we're switching bases is that we're going to designate another set of vectors to be our basis. Instead of the IJK was really easy, but sometimes we might be interested in having a different basis for some reason. And then this is right. But not necessarily 1, 0, 0. Okay. So that's I got a nice example for this too. We'll talk about it in a minute, but let's talk about the dimension of a subspace. The dimension of a subspace is the number of vectors in your basis, in your set of bases. Yeah, and we would say a zero-dimensional vector or vector space. So 0, remember 0 is a vector subspace for everything. We can say that 0 is that particular subspace is a zero-dimensional space, which makes sense because it's nothing. Yeah, because 0, we're talking about the 0 vector, right? Yeah. So when we're talking about the 0 vector, that doesn't span anything, and that's and for the 0 vector, remember our basis for that is the null set. So if we go back to this example, since we're here, let's go back to this example. Let's assign dimensions to these things. So in this case, this has dimension 0. It's a zero-dimensional subspace. Whoops. I'm trying to bold it. There it goes. Whoops. Okay. The next one. I just thought I'd change it up. That's the real reason. because if you're looking at these notes, you're just reading it, you know, in order, but then this is backtracking too. All right, so the space of polynomials is degree 2 or less. This is a three-dimensional vector space, vector subspace. And this one we already mentioned. The number of basis vectors. Basis, yeah. Because you want to know what dimension you're in. You're in the third dimension, you're in the second dimension. For polynomials, it doesn't really mean very much. But when we're talking about Rn, I think it would have a more meaningful meaning for us. Our first example, or example 2c, the basis turned out to be just one vector, so that's a one-dimensional example. Here's a two-dimensional vector space in GF23, and this one, GF23, is actually three-dimensional, which kind of makes sense because there's three components in each of these vectors. Right? All right. Let's see if we can do another example, and this time let's do examples in R2 and R3 where we can actually visualize things. See if I can draw now. I really need to draw. So remember our subspaces in R2? So our subspaces are all of R2, or our basic subspaces that we know should be there would be all of R2, our zero vector, and there's one other subspace that's a proper subspace. Do you remember what it was? One. Oh, that's for polynomials. So let's bring ourselves to R2 now, two-dimensional plane, x-y axis kind of business. Do you remember what the subspace was? So R2 is a subspace, the whole space is a subspace, the zero, the origin subspace, and there's one other subspace here. A line, there's one special feature of this line. Yes, that's the special feature. So I think last time I mentioned this, or we talked about this briefly, I mentioned this and then I wrote it as a set. Y equals mx, or to say it in words, I guess, line through the origin. I was going to say y equals mx, but that kind of excludes the vertical lines, unless you let m be infinity. But remember, if we talk about a line through the origin, as a vector space, vector subspace, then we're seeing it as a span of a vector that's on that line, right? So, ooh, I'm writing. Nothing's happening. No, I'm not changing colors. What happened? So let's take a look at an example, a line through the origin, and I can find a vector in here. What would that vector be? It would be y over x, m over 1, m, 1 m, right? 1, what? Is that right? Yeah, m over 1. Okay. So if this is my basis, that's my basis for this subspace, and that's it. And so I have a basis vector that describes my subspace. So zero's in there, and if I add two vectors on this line, I'm still going to get a vector on that line. And if I scale or multiply any vector on this line, I'm still going to be on that line. So that's good. And then this only has one vector in my basis, so it would be a one-dimensional subspace. So what we have here in R2 are three examples of subspaces. The whole thing is in R2 is a two-dimensional subspace, a zero-dimensional subspace, and your line is your only real proper subspace in R2. It's a one-dimensional subspace. Okay? So in terms of R2, you only really have three possibilities for subspaces. It's either the whole thing, zero, or a line passing through the origin. Okay? Any questions about that? All right, let's go to R3. So in R3, you have those, again, always subspaces, which is the whole vector space itself in the zero subspace. And then there's another subspace in R3, a line going through the origin. And what? Plane. So you can either have a 3D or a zero-dimensional subspace in our first two basic examples. A line going through the origin is a one-dimensional subspace. It'll be spanned by one vector. And the vector can be any point on that line. By point, I mean vector. Any vector on this line, you scalar multiply it, you're still going to be in that line. If you take any two vectors on that line, you add them, subtract them, scalar multiply them, it's still going to be on that line. Andrew? Yeah, so the R3 itself? Technically, that counts as the subspace. Yeah. But in terms of the definition, they say proper subspace. It's not technically a proper subspace because a proper subspace has to have less dimension than the original one. Yeah. In R3? No, because there's one more in the two-dimensional plane. So a plane passing through the origin, however we can try to draw that plane passing through the origin, is also a proper subspace. A subspace includes 0, scalar multiples in addition. So if we take two random vectors in there on the plane, if we add those two vectors, are we still going to be on the plane? Looks like it. Well, for my drawing, of course it does. But there's no way you can, if you have two vectors, there's no way you can jump out of the plane if those two vectors are already on the plane. Think about scaling them and subtracting them and doing all kinds of stuff to two vectors. If they are on the plane, then they stay on the plane. The only way we would get them up is that or down is if we add another vector that's not on the plane. But when we're doing subspaces, we only want to involve the things that are within the subspace. Okay? So that's two-dimensional. Yeah. Proper subspace? Well, we don't have improper per se, but we say proper to say that you have less elements in your subspace than you do in your original vector space. So R3 itself is a subspace, but it's not a proper subspace of R3 because it's everything. So if I want to knock off one of those vectors, then I'm down to two-dimensional, and that's a proper subspace. And then if I knock down another dimension, I'm one-dimensional, that's a proper subspace. And then 0, I mean, we don't really call that a proper subspace because it's a subspace for everything. I refer to it as a degenerate subspace because it doesn't generate anything. Degenerate's a good name. Oh, yeah. So. It was degenerate. Okay.
That were kind of rejected before and during World War II.
Wow. All right, let's see if we can throw in a few more ideas here. A matrix has a column space, subspace. It has a null space, and it also has a row space, which we really haven't talked much about. But in the book here, in this particular section at least, they introduced the column space and a null space. So the rank of a matrix is the dimension of the column space. So instead of saying the column space has dimension 2 or whatever, you can say the rank is 2. So when you say rank, It means that you're counting the number of basis vectors you get from your column space. Okay? The nullity is the dimension of the null space. If they did that, they should have called the first one the column-T. Column-T. No, that's not. The rank is also, by the way, rank is also the dimension of the row space. So again, we haven't talked much about row spaces, but the reason they call it a rank and the reason why it's important is that it's also refers to the column space, not just, or the row space, not just the column space. So the rank is also the dimension of the row space. So the nullity, you know how we find those free variables and stuff? However many free variables we have, the number of free variables we have is the nullity. Yeah. No, they're going to be the same. Yeah, so that's interesting because you can have a non-square matrix, right? And then you reduce it, and then you get like 3 pivot points or pivot columns. It turns out that you're also going to have 3 rows, even if, yeah, I mean, 3 non-zero rows. Yeah, we haven't talked about how to find the row space, but it's going to be the same. That's the really interesting part about this. There's the rank theorem, they call it. The rank theorem is adding, you can add, right? The rank theorem, if you add the rank and the nullity, it's going to equal to the number of columns. All right, let's think about that for a minute. And let's go to our example over here that we had. In this example, how many columns do we have? Yeah. The number of pivot columns, yeah. Yeah. So if we think about it that way, the rank is the number of pivot columns, the nullity is the number of free variables, right? When you row reduce it, the number of free variables and the number of pivot columns make up all the columns in your matrix. So in this particular example, we have 5 columns. Our nullity is 2 because the basis for our null space has 2 vectors. And our column space has, the basis for our column space has 3. So that's 3 vectors in our column. That's 3 dimensions for our column space and 2 dimensions for our null space. And so you add that together, you get 5, which is how many columns we have. So I think that's an interesting note if we just remember that the rank is a column space. The column space, the dimension of the column space or the rank is going to be the number of pivot columns. And the null is the number of free variables. And that's free variables come from columns, and then your n is a total number of columns. It does, doesn't it? Yeah, if you look at it this way, yeah. I hope so. And there's this basis theorem here. What's it say? H is a p-dimensional subspace of Rn, assuming that n doesn't equal to p. Any linearly independent set of exactly p elements in H is automatically a basis for H. Also, any set of p elements in H that spans H is automatically a basis of H. What does that mean? As an example, we took a look at R3, and our two-dimensional example over here says that these two vectors over here, these two green vectors span this space. I can pick, I don't know why I picked that, but I can pick any other two vectors that are linearly independent, and they would still span everything. And if they are in fact linearly independent, then they could also be a basis for this. So I can have different basis. I can have different sets of basis vectors that span the same subspace, as long as I'm within their parameters, their things. All right. There's one more thing. And some time ago, we started this invertible matrix theorem, and we went A through L. Now that we know about column and row and dimension and rank, we can add more. And if you're taking notes, maybe you just write M through R, because you already had written A through L if you were taking notes. So for the invertible matrix theorem, we have to go back to dealing with square matrices. First of all, it has to be an n by n matrix, so it can't be any of those rectangular matrix. Although the idea of row, column, space, and nullity and rank and stuff, they can apply to non-square matrices. But specifically for this theorem, because we're talking about invertible matrix, we're only dealing with a square matrix. So let's suppose we have an n by n matrix. If the columns of A form a basis for, if A is invertible, then the columns of A form a basis for Rn. So I have a 3 by 3 matrix, and I row reduce it, and then I don't get any pivot columns or anything like that, or I get 3 pivot columns, no free variables. Then I could take those 3 column vectors, and they would span all of R3. The column space is the whole thing. The dimension of the column is n, or R3 or whatever. The rank is the number of, what's the rank again? The number of the dimension of the column space. Yeah, so the number of vectors in your column space basis. There should be n of them. The rank is equal to n. Now the nullity is 0, and the null space has nothing in it except for the 0 vector. NUL means null space, and nullity is nullity. Okay, so all these refer back to all these statements are equivalent to all those past equivalent statements that talk about a matrix being invertible. All right. Whew. I'm going to assign quizzes online for you guys to do instead of taking. I mean, we're still going to have a quiz on Monday because I promised you a quiz on Monday. But I think from here on, I'll assign quizzes that are online, and they'll be like true, false, multiple choice quizzes. Yeah, so you can refer to your text or whatever notes. What? Oh. I'll take a look at it. All right.